Let's continue with moving charges and magnetism, also called as magnetic effect of electric current. So in that, the question number 4.14, they have given you have two coils. Okay, so the first coil is X and the second coil is Y. Both are having the same axis. Okay, the axis of both the coils is same, and these are the parameters given for X. These are the parameters given for Y. Now they are asking what will be the net magnetic field at the center of the coil. So to calculate this, the net magnetic field, what we require, so they have given the current flowing in X is going anti-clockwise and the current going in Y is clockwise. That means the direction of magnetic field will be different in both the cases. Now if you look at X is anti-clockwise. Now anti-clockwise means in this direction. Okay, so that means the magnetic field due to X will be along the positive X axis, and the current in Y is clockwise. That means it will be in the negative X axis. So the magnetic field due to Y will be in the negative X axis. So yeah. Now we have to find out what is Bx and what is By, and then we will find out the net magnetic field for this type of arrangement. Now depending upon which is greater, we will be subtracting the value. So this B can be equal to Bx minus By or By minus Bx depending upon which one is greater. Now what is B? So Bx is equal to mu naught into Nx into Ix divided by 2 times of Rx, that is the radius. So if we substitute the value, you will be getting 4 pi into 10 power minus 7 into number of turns in X is 20, current passing through this is 16 divided by 2 into 16 centimeters. So we will convert it into meters. So your answer will be, this is 10. So that is 4 pi into 10 power minus 4. Okay, so Bx is equal to 4 pi into 10 to the power of minus 4 Tesla. Similarly, we will calculate what is By. So the value of By is equal to, same formula we'll apply for Y. So you have 4 pi into 10 power minus 7 into Ny, that is 25, into Iy. So that is 18 divided by 2R. So 2 into 10 power minus 2. So once again, this will go 9 times. 10 power minus 2, 10 power minus 1. 25 into 4 is 100. So 10 power minus 1 going to the numerator. What answer will we get? By is equal to 100 pi. And we have one 9 also. So 900 pi into 10 to the power minus 7 minus 6, or we can also write 9 pi into 10 power minus 4 Tesla. This is By. So clearly By is larger than Bx. So therefore your B is equal to By minus Bx, or you can do the vector addition. Okay, so I can write Bx into I cap plus By into, or I can write Bx vector plus By vector, that is B. So B is equal to, what is Bx vector? Bx vector is equal to 4 pi into 10 power minus 4 in the positive X direction, and By vector is 9 pi into 10 power minus 4 into negative X direction. So when we add, when this minus sign will come here, so when we find the resultant, we are going to get the answer as 5 pi into 10 to the power minus 4 into minus I cap. Okay, so that means the net magnetic field is along the Y direction, and the value of the net magnetic field is 5 into pi. So 5 pi you can multiply and write the answer, or simply leave it as it is. Our next question is 4.15, required magnetic field. So they have given a setup. Okay, they are asking us to find out what will be, or how should I design the solenoid in order to get these parameters as what do you call that, satisfied. Okay, so required magnetic field, the magnetic field that we require from the solenoid is given as 100 Gauss, and it should be uniform for at least 10 centimeter. Okay, and the area, and for an area of cross section of 10 power minus 3 meter square. So you need a magnetic field, a uniform magnetic field of this much strength, which is uniform over this length, at least minimum this length. If it is more, well and good, but at least it should be uniform over this length and this area of cross section. Now the coil that we are using has the current capacity of 15 ampere. Okay, and the maximum number of turns that are allowed is 100 turns per meter. So they're asking us to design a particular solenoid. So what we are going to do, the magnetic field due to a solenoid is given by B is equal to mu naught Ni. Okay, so from this we will find out what is N into I equal to. So N into I is equal to B divided by mu naught. So that is nothing but B is the magnetic field. So 100 into 10 power minus 4 divided by mu naught, 4 pi into 10 to the power minus 7. So when you approximate it, okay, you are going to get almost 8,000 as an answer. Okay, so the approximated value is going to be 8,000. Now, what does this mean? The number of turns into current should give me 8,000. Okay, so this is 8,000 ampere meter inverse, that is a unit. So what we can do, we can select any combination of number of turns per unit length and the current such that it is obeying these two parameters. Okay, so let us say if we take I is equal to 10 ampere. Okay, say I is equal to 10 ampere. Then what will be the number of turns? So the number of turns must be 800 turns per meter. Okay, turns per meter. So we are satisfying both the quantities. Okay, both the current, maximum current capacity and maximum number of turns. And what about this, the length of the solenoid? So the length of the solenoid, you need a uniform field for 10 centimeter. So usually in a solenoid, in order to avoid the end effect, now you know very well in the ends of the solenoid the magnetic field will decrease. Okay, so in order to avoid that non-uniformity because of the ends, what we will do is we will take a very long solenoid. So the length can be anything, like if it is 10 centimeter, we can take 5 times greater the length. Okay, so you can take 50 centimeter in length. Similarly, you can take 5 times greater the area required. Okay, so I can take 5 into 10 power minus 3 as the area of the solenoid, so that inside there will be a small area, okay, of 10 power minus 3 and length 10 centimeter, where I can perform my experiment or whatever is required from the question. Okay, so they're asking us to find out, they're asking us to set up a magnetic field which will be uniform over 10 centimeter and 10 power minus 3 meter square area. Now remember, this question can have multiple answers, so there's no one proper answer for this, but the answer should be in such a way that it should satisfy all the conditions. Okay, so we can take 50 centimeter and the area can be taken as 5 into 10 power minus 3 meter square. So you can set up a solenoid whose length is 50 centimeter. You can take 40 centimeter also, you can 100 centimeter also, anything. Okay, even 100 is well and good, but 50 is like, okay, minimum 50 we can have. Okay, so 50 and the area is 5 into 10 power minus 3. The current passing through this is 10 ampere and the number of turns per meter is 800 as the answer. Okay, so this type of solenoid we are going to use to satisfy the required question. The next question, 4.16. They have given that the magnetic field due to a circular coil of radius r at a point on its axis x distance from the center is B is equal to mu naught n I r square divided by 2 into x square plus r square the whole power 3 by 2. This means there is a circular coil, okay, and along the axis of the coil you choose a point P which is at a distance x from the coil, and this length is capital R, that is the radius. Okay, now they are saying that at this point this is the magnetic field. So whether this equation is true or will it be valid if this point P is kept at the center? So usually what is the magnetic field due to a circular coil at the center? So we find that it is mu naught Ni divided by 2R. So they're asking us to check whether if in this equation, if we substitute the point P at the center, will we get this equation back? Okay, that is what they're asking us to check. So it's quite straightforward, this question. So B is equal to, now if the point P is at the center, okay, so if P is at center of the coil, that means x is equal to 0. So if I substitute x equal to 0 in this equation, what will I get? So B is equal to mu naught N I R square divided by 2 into 0 plus R square the whole power 3 by 2. Okay, now what is this? R square to the power of 3 by 2, which is nothing but R cube, and 2 R square and R cube will get cancelled by 2 powers, and the remaining term you will be getting mu naught N I divided by 2R. Therefore, it is the similar or the familiar equation for magnetic field at the center due to a circular coil. The same 4.16b portion is given that we have two coils, both of them are having the same radius, and the current flowing through both the coils is in the same direction. You have a point O at the middle of the two coils, and the two coils are separated by a distance of r. Now this type of arrangement we usually call this as Helmholtz coils. Okay, Helmholtz coil. Okay, now the speciality of Helmholtz coil is that the region from P to Q, okay, the region from P to Q in a Helmholtz coil is a region of uniform magnetic field. Okay, that only we have to prove in this question, whether the region from P to Q is a uniform magnetic field or not. Okay, so this is true only if D is very small when compared to R. Okay, so this will be true only if D is very small when compared to R. So the point where we will start the derivation will be by finding out the magnetic field at point P and finding out the magnetic field at point Q, and then saying that both are equal. Okay, so we can prove that the magnetic field will be equal along the line P to Q. Okay, so first we will begin with B at the point P. Okay, so mu naught N I R square divided by 2 into x square plus R square the whole power 3 by 2. This is our formula, isn't it? The general formula. Now you tell me the point P, okay, it is at what distance from the center of the first coil? So first we will write down what is the magnetic field due to the first coil. Okay, so the magnetic field due to the first coil B1 at the point P will be equal to mu naught N I R square divided by, see, this R is the radius of the coil, but this here, okay, this x square and this R by 2, this x square term is different. Okay, so here x is nothing but the distance between the center of the coil and the point P. Now here the center of the coil and point P is at what distance? Already up to O we have R by 2, and this portion is D. So what we can write x as? We can write it as R by 2 plus D the whole square plus, I'll put a square bracket here, plus what is this? R square the whole power 3 by 2. Okay, and this magnetic field will be, let us say, along this direction, or if you have taken along the clockwise, it will be in this direction. So the direction here doesn't really matter. One more thing here that we need to understand is, since both the coils are having the same direction current, okay, the magnetic field will be at point P and Q in the same direction. So we will be adding the magnetic fields. Okay, adding as in yeah, the direction of the magnetic field is not changing throughout the line. So the magnetic field at point P will be along, so if we let us assume that it is anti-clockwise direction, so the magnetic field will be along along PO2. Okay, and the same way we will write down what is the magnetic field. We'll expand this. Okay, due to on at point P due to coil 2. Okay, so magnetic field at point P due to coil 2, let it be B2. Now B2 value is equal to mu naught NIR square divided by 2 into. Now here you see the point P is at what distance from the center O2? So it is R by 2 minus D. Okay, so the x value here will be equal to R by 2 minus D the whole square plus R square the whole power 3 by 2. This one is also along PO2. Okay, so both of them are along the same direction. So at point P, what we will do is we will add these two magnetic fields. That will be the total magnetic field at point P. Alright, so at B, the total magnetic field is B1 plus B2. So we can just include, the common terms can be taken outside. So mu naught NIR square divided by 2. Okay, 2 I'll take common. And then here we have 1 divided by this thing. Okay, so 1 divided by, expand this term. So you'll be getting R square by 4 plus D square plus RD. Isn't it? A plus B the whole square formula plus R square. Okay, then plus 1 divided by, expand this term. So this term will be, I'll write it here, R square by 4, I hope you understand it properly, minus RD plus R square. Okay, now you check these terms. Now since we have taken the assumption D is far lesser than R, so what we can do is we can neglect D. Okay, so the magnetic field at the point P, I'll write it as B subscript P. So mu naught NIR square divided by 2 into, so this D can be neglected, D here also it can be neglected, and here we are having to the power of 3 by 2, so we'll write it, where will I write? To the power of 3 by 2. This one is also to the power of 3 by 2. Alright, so let me just write it down. 1 divided by R square divided by 4 plus R into D plus R square the whole power 3 by 2 plus 1 divided by R square by 4 minus RD plus R square the whole power 3 by 2. Now you have R square and R square term, so we can add those two. Yes, so R square by 4 plus R square is 5 R square by 4, and we can take that 5 R square by 4 common. So let us do it in one step or two steps. So BP is equal to mu naught NIR square divided by 2 into 1 divided by, now let me take the reciprocal. Okay, so I'll change the power as minus 3 by 2. Okay, so I'll write 5R square by 4 plus RD the whole power minus 3 by 2 plus again the same thing 5R square by 4 minus RD the whole power 3 by 2 minus 3 by 2. Okay, so here we will take 5R square by 4 common out. So when we take it common out, we will get a power minus 3 by 2 also there. Okay, with us. So BP is equal to mu naught NIR square divided by 2 into, now I am taking that to the denominator. So 5R square by 4 the whole power 3 by 2 is taken common out from both the two equations, and here I'll be writing, so this will be equal to 1 plus this divided by this 5R square by 4. Okay, so what will I get? RD divided by 5R square by 4 means 4 by 5 RD divided by R square. Okay, this thing the whole power minus 3 by 2 plus same thing here 1 plus 4 by 5 minus 4 by 5 RD divided by R square the whole power minus 3 by 2. Now I know this is really confusing, but if you do it on your own you will get it. Okay, so here we have to apply the binomial theorem. Okay, so binomial theorem means what? This is 1 plus x the whole power minus 3 by 2, and this x is very small, so therefore we can apply the binomial theorem and we will neglect all the other terms and keep only the first two terms, which is 1 plus nx. Okay, so the binomial expansion goes like 1 plus x the whole power n is equal to 1 plus nx plus all the terms, those terms we are going to neglect. So BP is equal to mu naught capital N I R square divided by 2 into 5 r square by 4 the whole power 3 by 2 into 1 minus 3 by 2 into 4 by 5 rd divided by r square. Okay, then plus 1 plus 3 by 2 into 4 by 5 into rd divided by r square. So here clearly we can see these two terms are getting cancelled. Simple as that. Okay, so after this I'll erase the board and then we'll continue. So continuing from where we left, so BP is equal to 4 pi into 10 power minus 7 mu naught into n they have not given into I into r square divided by 2 into what is this 5 by 4. So I'll write 5 by 4 to the power of 3 by 2 into r square to the power of 3 by 2, which is nothing but r cube. So I can, and here we are having 1 plus 1, so multiplied by 2. So this 2 gets cancelled and we will be left with 1 r here in the denominator. So the answer will be, now if you calculate all the numbers, that is 5 by 4, power 3 by 2, 4 pi, 10 power minus 7, your final answer that we need is actually 0.72 is approximately equal to 0.72 mu naught Ni divided by R. Okay, and this is exactly what they are asking us to prove. Now they have not cancelled this 2. Okay. So they have taken it in the multiplication. So we will write it as 2r. Okay. So this value, okay, this 4 pi 10 power minus 7, this 2 and this 5 by 4 power 3 by 2. You calculate numerically, you are going to get 0.72 into mu naught Ni divided by 2r. Okay. Oh, sorry, mu naught is not included. So just a small mistake. So this is 4 pi into 10 power minus 7 isn't included. So you just have 5 by 4 power 3 by 2 into 2. That's all we have to do, and the rest is just given directly in the question. So this is what we have to prove in the question. Since I'm not calculating, all these confusions are coming. Okay, yes. So that is your answer. Basically this is your equation. Okay, so numerically you have to prove that is equal to this. Okay, so whatever as they have given in the question, you need to frame the answer like that. The next question is 4.17. The question they have given, you have a toroid whose inner radii or radius is 25 centimeter, okay, and outer radius is 26 centimeter. The toroid has 3500 turns and it is wound over a non-ferromagnetic material. That means we can assume that it's basically there's no material at all. So the permeability inside the toroid is going to be mu naught, that is air or vacuum. Okay, and the wire carries a current of 11 ampere. Now we have to find out the field inside the toroid, inside the core of the toroid and outside the toroid. Okay, so we have to find out inside the core of the toroid and outside the toroid. Now by theory, you know clearly inside and outside the toroid the field is 0. Okay, the magnetic field due to a toroid is equal to 0, and inside the core of the toroid the magnetic field is given by B is equal to mu naught small n into I. That's it, as simple as that. Okay, so here mu naught is equal to 4 pi into 10 power minus 7 and small n represents number of turns per unit length. So the number of turns is 3500 per unit length. Now in case of toroid, what we have to do is we have to find out the circumference, because here that is the length of the toroid is the circumference of the toroid. So since they have given two radii, okay, 25 and 26 centimeter, so we will be taking the average of this, which is 25.5 centimeter. Okay, so the circumference will be 2 pi into 25.5 into 10 to the power minus 2 multiplied by current, which is 11 ampere. Okay, so you will be getting, this will go 2 times, and once you cancel this all, you are going to get the magnetic field as, I'm not going to do the calculation, just the final part is equal to 3.02 into 10 to the power minus 2 Tesla. So this is the magnetic field inside the core of the toroid, and inside and outside the toroid it's going to be equal to 0. That's all. Question number 4.18 says that there are 3 sections. The first one, A, it goes like there's a magnetic field which varies from point to point. Okay, but the direction is same. A charged particle goes undeflected with constant speed. What can you say about its initial velocity? Now, when we studied the theory part, we saw that the magnetic field, okay, will create a force which is called as a Lorentz force on the charged particle moving with the velocity v. But the point there is the charged particle should be at least at some angle with the magnetic field, or it should be fully perpendicular. Okay, so but in this case, since the velocity is not changing, the particle is moving with a constant speed. Okay, so that means that there is no force acting on the charged particle. So if no, when can we say that no force is acting on a charged particle? So you know force is BQV sine theta. Okay, so if there is no force acting on the particle, that means theta value should have been, B is not 0, Q is not 0, V is not 0. So that means sine theta only should have been 0. That means theta should take values 0 or 180. So the charged particle is either in the direction of the magnetic field, or it is either anti-parallel to the magnetic field. So the charged particle is parallel or anti-parallel to the magnetic field. That is why it goes undeflected and its velocity also remains constant. So there is no change in the charged particle the way it moves. So the initial velocity of the charged particle is what? It's undeflected. The B portion of 4.18 says that a charged particle enters a non-uniform magnetic field, and because of the non-uniform magnetic field, meaning the magnitude and direction, everything is different at different points, it goes in a complicated trajectory, meaning at every point the force that is acted upon on the charged particle will be varying. Okay, so it goes in a complicated trajectory, and if no collisions take place due to the course of the movement of the particle, then will the final speed be equal to the initial speed? So that is what they are asking. Now, when a charged particle experiences a force due to a magnetic field, it is always perpendicular to its velocity. Okay, so there is a concept, it's always perpendicular to its velocity, because we know F is equal to V cross B, meaning the force is always, it's a cross product, V cross B, it's a cross product. That means the force should always be acting perpendicular to the velocity vector. Now, that is a plane containing V and B both. Okay, so that means the force is perpendicular, so there is no work done on the charged particle, and if no work is done, that means the velocity of the particle, the velocity will change, that is the direction will change, but the magnitude will remain constant. So yes, the final speed will be equal to the initial speed of the particle. Okay, so doesn't matter which particle is entering or leaving, the final speed is going to be equal to the initial speed, because the force is perpendicular to the velocity, and perpendicular forces do not do any work on the particle. Question number 4.18C section is given that an electron travels from west to east direction and it enters a chamber with uniform electric field in the north to south direction. What must be the direction of the magnetic field in such a way that there is no deflection on the electron? Okay, so imagine you are having a plane. Okay, now on this plane you have the electron which is traveling from west to east direction. Okay, and the electric field is from north to south direction. Now we know very well an electron always travels towards the positive potential of the electric field. So if electric field is from north to south, that means the electron will be deflected towards the north direction. Okay, now to avoid this deflection, to cancel this deflection, the magnetic field should deflect this electron along the south direction. Am I right? So the electron is being deflected by the electric field towards the north. So in order to cancel that, we need the magnetic field in such a way that it should deflect along your direction, that is towards you. Okay. So how will we find out the magnetic field required? So the magnetic field that will deflect the electron along the south direction will be given by the left hand rule, and usually we use the left hand rule to find out the Lorentz force, but here the Lorentz force is already given, that is we want the electron to be deflected towards the south. So the south direction should be the force, and the electron is traveling from west to east. Okay, so the current will be traveling from east to west. So we take this as this direction is, am I right? It's traveling from west to east, direction of the electron. Yeah, the middle finger should point from west to east. That means my index finger will be pointing towards the downward direction. Okay, so I can't twist my hand. Okay, so yeah, so this is pointing towards the south. That is a force acting on the conductor, on the electron, and the electron is traveling from west to east. That means the current is taken from east to west. Okay, and then therefore the magnetic field is pointing along the downward direction. Okay, so the answer for this question is, if the magnetic field is along the downward direction, then the deflection in the electron will be zero. So the deflection due to the electric field will be cancelled by the magnetic field. So that is the answer for 4.18. See, that is the end of this question. So moving on to the next question. So in the next question, they have given that there is a magnetic field whose strength is 0.15 Tesla, and on this magnetic field you are sending an electron through a heated cathode. Okay, and the potential of that cathode per electrode is 2 kilovolt. So 2 into 10 power 3 volt. Now, what is the connection between voltage and the electron? Okay, so the velocity of the electron depends upon from what voltage it has been ejected. Okay, how they are related? So you know very well, voltage is equal to work done by charge. Okay, the potential of anything is equal to work done by charge. So here, what is work done? Charge into voltage. Okay, and we can equate this work done to the kinetic energy of the electron. So we get half mv square is equal to E into V, that is charge into voltage. So from this equation, V is equal to square root of 2eV divided by m, and when we substitute the values, 2 into 1.6 10 power minus 19 into potential 2 into 10 power 3 divided by m value is 9.1 into 10 power minus 31. Okay, so once you calculate this, your answer is 2.65, I think. Yes, you calculate it using the log book or calculator. 2.65 10 power minus 10 power plus 7 meter per second. So with this high velocity, the electron is ejected in the presence of a magnetic field in two different cases. So in the first case, they are sending it transverse to the magnetic field, meaning if the magnetic field, let us say, is in this direction, then the electron is sent in a perpendicular direction. The velocity of the electron is along the perpendicular to the magnetic field. Now in that case, the force will be maximum, and there's one more thing here. Whenever a charged particle is perpendicular to the magnetic field, only one force is acting which is perpendicular, okay, to the charged particle, to the velocity of the charged particle. Therefore, the particle will execute a circular path. Okay, the particle will execute a circular path. So the radius of that circular path is given by, now in the question they're asking us to find out the trajectory. Meaning what? Meaning you have to say what shape the particle is traveling, and if we have found the shape, then we can also find out what is the radius of that circular path. So R is equal to mv by bq. Okay, R is equal to mv by bq. Now mv by bq means what is b here? What are the parameters that is given? The substitute. So 9.1 10 power minus 31 into v. V is this 2.65 into 10 to the power of 7 divided by b. B is 0.15 into Q. Q is the charge of the electron, that is 1.6 into 10 power minus 19 coulomb. So the answer is the radius of the electron is approximately 1 millimeter. Okay, so the electron will be deflected, and it will be deflected in such a way that it is going to make a circular path, okay, along the magnetic field. So always remember, see, if this is a magnetic field and if the electron, let us say, was traveling like this, now it will be deflected in a perpendicular direction. Okay, so perpendicular direction means it will start making a circular path around the magnetic field. Okay, now in the second question, they are asking what will be the trajectory if the magnetic field and the velocity of the particle is at an angle of 30 degrees. So instead of 90 degrees, now the velocity and magnetic field are kept at 30-degree angle. So what will happen in that case? Now in theory we have already discussed, whenever we have this type of inclined or oblique velocity and magnetic field, the velocity can be resolved into two components, that is v cos theta and v sin theta. Okay, and you know very well the velocity which is along the same direction as that of the magnetic field will not contribute to the Lorentz force. Only the velocity which is perpendicular, the perpendicular component alone, will be contributing to the Lorentz force. Okay, then what will this v cos theta do? What is the job of this v cos theta? It will make the electron to move in a forward direction. Okay, so for example, if the velocity is along 30 degrees to this axis, and if the particle is having v sin theta along this direction, okay, so you're having the velocity is ejected in a angular path. So what will happen? So the particle, okay, will still make a circular path, but now you are having a horizontal velocity also. So the particle along with the circular path will begin to move along the horizontal, along the rectilinear direction also, or what do you say that? What is the way? Straight line path? Translatory. Yes, so the electron will start moving in a translatory as well as a revolving motion. So we can say that it will move like this, okay, and this is a helical path. This is a helical path, and the radius of this helical path will be given by mv perpendicular, okay, perpendicular divided by BQ. So if we substitute this, what answer we are going to get? So 9.1 into 10 power minus 31 into V perpendicular means what? V cos theta. So 2.65 into 10 power 7 into cos 30. Okay, so cos 30 is equal to root 3 by 2. So we'll substitute all that, and 0.15 into 1.6 into 10 power minus 19. So the R, that is the radius of the helical path, is equal to, the answer is 0.50 millimeter. So this time the radius is smaller than the last time. Okay, but there are two types of velocities, and therefore instead of along with the circular, there will be a translatory motion also. Okay, so that's it for this question. The next question 4.20 is that you are having a charged particle which is sent or ejected from a high potential high potential source, which is equal to 15 kilovolt. Okay, 15 kilovolt, and here the magnitude of the Helmholtz coil is set up. Okay, so you're having a Helmholtz coil. This question has nothing to do with the Helmholtz coil, don't worry. Okay, but you're having a uniform magnetic field over a small region. That's what they're trying to say. So as I explained already, Helmholtz coil is used to set up uniform magnetic fields for a small portion of the whatever experiment we are going to do. Okay, so our experiment will be conducted in this small region. We have already established that in this region the magnetic field is going to be uniform. Okay, so I think I forgot to mention in that question, yeah, the point P only we had calculated, isn't it? So in point Q also the magnetic field will be same. Okay, because that point Q also will be R by 2 plus D, and from that other coil it will be R by 2 minus D, and then the same thing we will derive, and then we will say that it is the same at P and Q. Therefore the field is uniform over the area. over the linear length 2D. Okay, so you had that two coils, isn't it? And that both the coils center point was O, and you had P point and Q point. So at P alone, I think we found out. I think I forgot to mention Q. Yeah, so you just note it down. Okay, so at P and Q both points, the magnetic field is going to be same, because it's the same type of derivation only that we are going to do for Q. Okay, so therefore the entire region, the magnetic field is going to be uniform. So any experiment where you want a uniform magnetic field, you can use Helmholtz coil. So the same thing we are doing here. Okay, and the magnetic field that is created is actually B is equal to 0.75 Tesla. 0.75 Tesla, and they have not mentioned which particle is entering, so we have to guess the particle. Okay, now they are saying that there is an electrostatic field also perpendicular to this magnetic field. That means we will be having, okay, that means we will be having an undeflected path, okay, for a particular velocity. So the velocity for which the path is undeflected is E by B, and the electrostatic field is given as 9 into 10 power 5 volt per meter. 9 into 10 power 5 volt per meter. So V is equal to 9 into 10 power 5 divided by 0.75 Tesla. So the answer is velocity is equal to 12 into 10 power 5 meter per second. Okay, now for this velocity, okay, this velocity is coming from this potential. So you have half mv square. The kinetic energy of the particle is going to be equal to q times v. Okay, and you can substitute half into v square divided by capital V, okay, is equal to q by m, that is the charge by mass ratio. Now charge by mass ratio is very important for any particle. You can easily, guess the particle, or there are some certain properties if for a particular charge by mass ratio. Okay, so you have q by m, that is equal to half into, what is v square? So v square is this 12 into 10 power 5 the whole square divided by potential, that is 15 into 10 to the power 3. So the charge by mass ratio you are getting 4.8 into 10 power 7 coulomb per kg. Okay, now this charge per mass ratio is seen in deuterons. Okay, so the particle can be deuteron, but it is not the only particle which has this charge by mass ratio. So you have other particles which are helium 2 plus, lithium 3 plus, etc. Okay, so helium 2 plus, lithium 3 plus, all these particles also will have the same charge by mass ratio. Therefore, it can, in this particular problem, it could have been any of these particles. With that, we will end with this problem. We will end this session, and the remaining questions will be discussed in the next video. Thank you.